Hello everyone, thanks for listening to my talk and thanks to the organizers for giving me the opportunity to present my work at this conference. I'm Annagrazia Puglisi, I'm a postdoc at Durham University, and today I will present some recent results about sub-millimetre compact galaxies at high redshift. One of the central questions of galaxy evolution, and also the main focus of this conference, is understanding how do bulges and spheroids form. Mergers are one of the accredited channels for bulges formation, but these instabilities associated with the high gas fractions observed in high redshift galaxies have also been proposed as a viable mechanism to explain the formation of bulges. So there seems to be common the idea that we really don't need mergers to explain structural evolution in galaxies. And the idea that mergers are relatively unimportant for structures formation is supported by the existence of the so-called main sequence, which is a tight correlation between the stellar mass and star formation rate that we observe basically since redshift 6. This idea is also supported by observations in the optical near-infrared, showing that galaxies at high redshift along the main sequence have extended rotating disks. And this can be clearly seen in this plot, showing velocity maps of galaxies in the stellar mass versus star formation rates plane at redshift 1 from the CHEMOS 3D survey. And this shows that there is quite a good regularity of disks along the main sequence. On the other hand, to fully understand how galaxies are building up the structures, we need to study the molecular gas. The molecular gas is a key component of galaxies as it provides the raw fuel for future star formation. And another important point, which I think is quite relevant for understanding bulges formation, is that it allows us to have a view on star formation episodes that is unaffected by dust. And I think that this is quite important if we want to understand the origins of bulges, since the formation of those dense stellar structures is likely associated with compact star formation in dusty regions. Therefore, optical near-infrared surveys may miss this formation of galaxies. So finally, studying the physical properties of the molecular gas can give us clues about the processes that trigger star formation in galaxies. So in this context, to understand star formation and structures growth in galaxies, we conducted with ALMA a survey of 123 galaxies on and above the main sequence at redshift 1.3. This is a key epoch for galaxies and structures formation, as this is when present-day galaxies were forming most of the stars, and the Hubble sequence starts to emerge. Our study targets galaxies with star formation rate and stellar masses similar to the average star-forming population at the same redshift, as can be seen from this plot showing the distribution of the sample on the main sequence. Our galaxies have masses between 10 to the 10 and 10 to the 11 solar masses, which suggests that many of the objects that our study targets are likely to be the progenitors of redshift 0 bulgy disks, such as the Milky Way or Andromeda. The strategy of this study has been to observe with ALMA multiple carbon monoxide and neutral carbon lines in a large sample. And this allows us to sample different phases of the molecular gas and study its physics in details and with large statistics. Also, we conducted ALMA observations with moderate resolution, and this has allowed us to measure molecular gas sizes in a large sample. So in the rest of the talk, I will focus on those molecular gas size measurements in connection with other properties of the sample, and I will discuss the implication of our results for the formations of bulges. So this slide summarizes the method that we adopted to measure sizes. We measured sizes in the UV plane with circular Gaussian profiles by combining observations of individual tracers when they were significantly detected, meaning that their flux signal-to-noise ratio has to be larger than 5. And the plot shows the amplitude as a function of the UV distance for a galaxy in the sample, where we have reliable detections of two CO transitions and the underlying continuum. So the key point that I want to make here is that combining observations allows us to obtain size measurements of upper limits for 89 galaxies, which is quite a good statistics for those kind of studies at high redshift. The other key measurement for this talk is the measurement of stellar sizes. That we measure it from K-band images that trace the rest frame near-infrared emission in the sample, hence the stellar mass extent. The K-band images have similar resolution to the ALMA observations, and we measured K-band sizes also using circularized Gaussian profiles. This means that the method that we apply to measure molecular gas sizes and stellar sizes is very similar, and this allows us to easily compare those two quantities. So now this plot shows the correlation between the galaxy size and the stellar mass for the sample. The left panel shows K-band sizes, while the right panel shows sub-millimetre sizes from ALMA. And in both panels, the blue line and shaded area shows the mass size scaling relation and its scatter from optical near-infrared observations at redshift 1.3. Most objects here look like typical disks in the K-band, being located in the scatter of the mass size relation. On the other hand, many objects are smaller in ALMA that one would expect from the mass size. And we find in particular the 30% of the sample, here highlighted in red, have molecular gas reservoir that is 3.4 times smaller than the stars. Now, this plot shows the star formation rate as a function of the stellar mass for our sample. And the color code shows galaxies with an extended molecular gas reservoir in blue and galaxies with a compact molecular gas reservoir in red. So the sub-millimetre compact galaxies in our sample are distributed on and above the main sequence. And they are abundant at high masses, being 50% of the main sequence population above 10 to the 11 solar masses. So our measurements suggest that a sizable fraction of typical star-forming galaxies are building up a dense stellar core in a more extended stellar structure. So the next interesting question at this point is understanding what caused galaxies to have such a compact molecular gas reservoir. And to answer this question, we studied the molecular gas properties of the sample as a function of the main sequence position and as a function of the compactness. Now this plot shows the CO5 over CO2 ratio as a function of the main sequence position. And the color code highlights the sub-millimetre compactness of the sources as in the previous plot. The CO5 traces the dense molecular gas, while the CO2 traces the less dense molecular gas. Therefore, the CO5 to CO2 ratio traces the relative amount of dense to diffuse molecular gas in galaxies, and hence allows us to measure the excitation conditions in our sample. So this plot shows us that sub-millimetre compact galaxies on and above the main sequence have enhanced CO5 to CO2 ratios, suggesting a larger excitation with respect to the main sequence population. Now, this plot is quite similar to the previous one, but in this time, the y-axis shows the CO2 over LIR ratio. Because the CO2 traces the least dense molecular gas, it's a good proxy for the total molecular gas mass of galaxies, whereas LIR is a measurement of the star formation rate. Therefore, the ratio shown here measures the depletion times or the reciprocal or of the star formation efficiency. So this plot shows that sub-millimetre compact galaxies on and above the main sequence have low CO2 over LIR ratios, suggesting shorter depletion times or enhanced star formation efficiency with respect to the parent main sequence population. So the final ingredients that we wanted to add were measurements of the gas fractions. So this plot now shows the gas fraction as measured from the CO2 to 1 emission line flux. So we find that the gas fraction for our overall sample increases as a function of the main sequence offset, as we would expect from literature scaling relations that link those two quantities. However, when we look at the main sequence population, we find that on average, sub-millimetre compact galaxies on the main sequence have reduced gas fractions. And here I would like to point out that to measure gas fractions, we assume a starburst CO2H2 conversion factor for compact galaxies overall, and a disk-like CO2H2 conversion factor for extended galaxies. And as this is supported by the study of the ISM conditions that we conducted. However, the systematic difference in the gas fractions that we find is somewhat dependent on this assumption. Well, I would like also to add that those results are, the results shown here are confirmed by different molecular gas tracers and by the pure observable relations. Now, I do not have time to enter into the details of those assumptions, but I'd be happy to chat more about this offline. At this point, I think that it is a good moment to wrap up and to summarize our results. So all in all, our results can be consistently interpreted in the context of an evolutionary scheme that we summarize in this cartoon, showing the gas fraction as a function of the main sequence offset. So according to our proposed evolutionary schemes, galaxies sitting on the main sequence at high redshift have an extended molecular gas disk with relatively high excitation associated with the high star formation rates that we observe at high redshift. But we believe that mergers drive gas to the center, ignites a starburst, and drive a galaxy above the main sequence. Here, the galaxy has a compact star-forming core, high star formation efficiency and excitation. And the gas in the space gets rapidly consumed during the starburst. And this causes the galaxy to go back to the main sequence. So in this context, we believe that sub-millimetre compact galaxies on the main sequence represent the final stage of the sequence and are caught in an early post-starburst phase after the merger-driven starburst episode. At this stage, the galaxy retains the memory of the merger, having a compact gas and enhanced efficiency and excitation, but has a reduced gas content as a result of the previous starbursting phase. So to conclude, we studied the structural and interstellar medium properties of galaxies on and above the main sequence at redshift 1.3. We found that 50% of the massive main sequence galaxies population have compact sub-millimetre sizes, on average 3.4 times smaller than the stellar extent. And this suggests that a large fraction of typical star-forming galaxies at redshift 1.3 is building a dense stellar core. Those sub-millimetre compact main sequence galaxies have high molecular gas excitation, short depletion times, and high star formation efficiency. Also, those objects have systematically reduced gas fractions with respect to the parent main sequence population. So we interpret our results in the context of an evolutionary sequence in which sub-millimetre compact main sequence galaxies are an early post-starburst population following a merger-driven starburst episode. Therefore, this to answer to the main question of this conference, this study is suggesting that mergers may have an important role in the formation of bulges and spheroids. And this is all for me. Thanks a lot for your attention.